So in the previous lecture, we have seen how to calculate symmetry adapted linear combinations of 1s orbitals of hydrogen for water molecule. So let us now take one more example so that the method is very clear in our heads. So let's start. So what we will do is we will take another example to again develop SALCs using 1s orbitals only. And then we will go to more complex example where we'll be dealing with 2D representations. So let's start with the SALCs belonging to sigma bonding in C2H4. Okay, so what we will be doing here is we will be calculating using 1s orbitals of the 4 hydrogen atoms. Okay, so first and foremost thing is to orient the molecule in Cartesian coordinate system. That way it will be easier to operate symmetry operations onto this. So this is done. So now how do we draw this? So we have X, Y, and Z, and so you have CC double bond, which will be lying along the Z axis, and we will have 4 hydrogens, right? Like this. Okay. So now, if we do that, we can give each 1s orbital as some nomenclature. So for example, let this be called as sigma 1, sigma 2, sigma 3, and sigma 4. So now the second step is to identify the point group. So I'm not going to go into all the details. I will just skip the steps which we have already learned. So identify the point group of this molecule, and to know the point group we should list down all the symmetry operations and find out the point group. So you know all the steps here. So I'll just directly write the answer here. So this will be D2H point group, because there is one C2Z and then 2 perpendicular C2s, which is C2X and C2Y. So this goes to D category, and then there is a sigma H plane. Well, in this case it will not be called as sigma H, but it will be called as sigma X, sigma Y, and sigma Z. But there is one plane which is perpendicular to the principal axis, and hence it will be called as D2H point group, right? So let's not go into those details. We have already discussed this molecule itself before. Now what we'll do is use the 4 1s orbitals of hydrogens as a basis and develop a representation under D2H point group. So when I say that, what do I mean? So that means I'm going to find out the matrix representation under all symmetry operations. All right. So now let us list down the symmetry operations we have. So this is D2H, and what we are trying to do is we are trying to create tau sigma, right? Sigma 1, sigma 2, sigma 3, sigma 4. And the first is E, then we have C2Z, then we have C2Y, C2X, then we have, what else do we have here? We will have, I think I will be there, yeah, 2. Then you have sigma x, sigma y, sigma z. Right? Anything else which I'm missing? No, I think that will be all. Or sigma, this will be sigma x y, y z, z x, right? Okay, so now we need, using sigma 1, sigma 2, sigma 4, 3, sigma 4 as the basis, that we need the matrix representation under all of these symmetry operations. So to do that, we need to operate E onto, let's say if we do that, sigma 1, sigma 2, sigma 3, sigma 4, and what is the resultant of this? Resultant is same, sigma 2, sigma 3, sigma 4. So this would imply that my E is a unitary matrix of order 4, right? Let's do the same thing for next operation. Let's say C2Z operation. So if I do sigma 1, sigma 2, sigma 3, sigma 4, and if I do a C2Z operation, what is the resultant which I'm going to get here? So C2Z applied on sigma 1, that will give you sigma 4. So I'm rotating around this anti-clockwise. So that means sigma 1 and sigma 4 will be replaced, and sigma 2 and sigma 3 will be replaced, right? So sigma 2 will be replaced with sigma 3. So sigma 2 is going to sigma 3, sigma 3 is going to sigma 2, sigma 4 is going to sigma 1, right? So this would imply that my C2Z has a matrix representation which can be written as 0, 0, 0, 1. Then you have 0, 0, 1, 0. Then you have 0, 1, 0, 0, and 1, 0, 0, 0. So now you can try yourself by doing this multiplication with this and see if you are getting this, right? So basically what I have done is I have placed 1 over where sigma 1 is going to its new position. So sigma 1 is going to sigma 4. So I have placed 4 over here. Now sigma 2, that is the second row, sigma 2 is going to sigma 3. So I have placed 1 here. Similarly, sigma 3 is going to, that's third row, is going to second position. So sigma 2. So that's why in second column I have placed 1. And sigma 4 is going to sigma 1, right? So let us see that more carefully with other operations also, so that it is very, very clear. So again, let's say if we are now applying C2x, so we have sigma 1, sigma 2, sigma 3, sigma 4. What happens here if we do this? So if we do this, let me go back to the molecule again. So now we are rotating about this, right? So that means now sigma 1 will go to sigma 3, sigma 2 will go to sigma 4, right? So sigma 1 is going to sigma 3, sigma 2 is going to sigma 4, and sigma 3 is going to sigma 1 and sigma 2, right? So this implies that my C2x is, so now my C2x is, so sigma 1 is going to sigma 3. So that means I will put 1 at third position. Now sigma 2 is going to sigma 4. So I'll put 1 at fourth position. Sigma 3 is going to sigma 1. So I'll put 1 here. And sigma 4 is going to sigma 2. So I'll put 1 here, right? So this is very, very clear. And you can again test it by multiplying this with this, and then you should get the resultant matrix. Okay, so similarly, so let's not do this all over again. So I'll just write down the matrices for C2y and rest of the symmetry operations. So I will have 0, 1, 0, 0. Then I have 1, 0, 0, 0. Then I have 0, 0, 0, 1. and I have 0 0 1 0. Okay, and then for I, this will be, so whatever is replaced with what, so you have 0 0 1 0, and you have 0 0 0 1, you have 1 0 0 0, and you have 0 1 0 0. Similarly, you have for sigma x y, which will be, so I suggest you all do this by yourself, so that it is very very clear. Otherwise, by just looking at it, it will not go into very deep. Okay, so 0 1 0 0 1 0 0 0. So why we are writing these matrices, I will tell you. We need the trace of this. You have 0 0 0 1. Okay, so now that we are done writing all the matrix representation, what we have to do is we have to find out the trace and put that trace here. That will give us the reducible or irreducible representation, right? So now let's write the trace. So trace for E is going to be 4. Trace for C2Z is going to be 0 because all the diagonal elements are 0 here. Then C2Y also it is 0. C2X also it is 0. I will be 0. Sigma XY will be 0. Sigma YZ will be 4. And sigma XZ will be 0. Right? So this is what we have got as the reducible representation now. So before we actually go to fourth step, let me give you a way of writing directly the traces without having to write all the matrices. So easier way to write traces without, but you should know how to write the matrix, okay, so that if it comes to that you should be able to do that. But there is actually no need to write the full matrix and then find out the trace. There is a much easier way. You can just look at it and write it. I will just tell you without writing the matrix representation for each symmetry operation. Okay, so the method is basically it's a thumb rule. So I will just quote that: any basis function that moves under symmetry operation contributes nothing to the trace or character. Otherwise, it contributes 1. Okay, so let us see that again. What do I mean by that? So when I apply E on the basis function, none of the basis functions move. That means all of them will contribute 1 for the trace. That will give you trace 4. If I do C2Z, all 4 will move. That means they will not contribute anything towards the basis, towards the character or trace. So the trace will be 0. Again, everything will move here. Everything will move here. everything will move here, everything will move here. Now sigma yz, if you carefully look, sigma yz is the plane which is the molecular plane here, right? So if we do sigma yz, sigma 1 stays where it was, sigma 4 stays where it was, sigma 3 and sigma 2 stays where they were, right? So that means none of this move. So that is, they contribute 1 towards the trace. So that character under sigma yz will be 4, and rest everything will be 0 except E, right? So this is much easier way. So now next is to calculate the reducible representation, irreducible representation. So step number 4 is reduce tau sigma to its component irreducible representations using reduction formula. So at this point, I don't think I need to remind you what is the reduction formula. You should be well aware of this. So by reduction formula, and I'm not going to do that calculation either. So look back the previous notes and see what is the reduction formula and how do I use that to reduce sigma, tau sigma into the following. So if I do that, I will get AG plus B3G plus B1U plus B2U. So I have got 4 representations. There were 4 basis sets, so 4 1D representations will you will get. So the linear combination of this will be tau sigma, to which the 4 sigmas are forming basis of. So now 5th step is to apply projection operator. So aim is to find out the linear combination which will have these 4 symmetries, right? So apply projection operator for each of the IR representation obtained in step 4. So you don't have to consider all the IR representation of T2H point group. You have to consider only those which are coming as a result of reducing this reducible representation, which was in turn formed using sigmas, 4 sigmas as the basis. Okay, so only those representations you have to consider. Other representations, even if you consider, they will turn out to be 0, so there would not be any contribution coming from other representations. We can test it out if you want to. Okay, so each of the representation to any of the basis set function. So what do I mean? So let's say if I want to find out what is the linear combination of the basis which has symmetry as AG, so I will apply projection operator corresponding to AG onto sigma 1. Okay, so you can choose any of these basis function. They will give you all same result. So it does not matter if you start with sigma 1 or sigma 2 or sigma 3 or sigma 4. Okay, so now what do I have here? So remember that the formula is L by H. So L is the dimension of this representation, which is 1, and H is 8 here. That's the order of the group. Then what you have to do is you have to take out from the character table what is the character under AG representation, that is 1 into E symmetry operation, effect of E onto sigma. Similarly, 1 into C2Z sigma 1 plus, so the AG is a totally symmetric representation, so all the characters are going to be 1. So that's why I don't have to look at the character table here. But for other symmetry operations, other IR representations, you will have to look at the character table. C2Y applied on sigma 1 plus 1 into C2X applied on sigma 1 plus 1 into I applied on sigma 1 plus 1 into sigma xy applied on sigma 1 plus 1 into sigma yz applied on sigma 1 and so on. Sigma zx applied on sigma 1. So again, it is not required for me to do this complete calculation for you. So you can, I'll just give you a couple of solutions. So if you do apply E on sigma 1, you will get sigma 1. If you apply C2Z on sigma 1, so let us again look back. So if you apply C2Z on sigma 1, you will get sigma 4, right? Similarly, if you apply C2X on sigma 1, you will get sigma 3. If you apply C2Y on sigma 1, you will get sigma 2 and so on, right? So the resultant of this is going to be 1 over 4 sigma 1 plus sigma 2 plus sigma 3 plus sigma 4, okay? And this upon normalization you can write this as 1 by 2 sigma 1 plus sigma 2. Remember, we need to develop orthonormal sets, okay? So this has to be normalized. Sigma 3 plus sigma 4. So this linear combination would form basis for AG representation, and this is going to be normalized, right? Okay. Now let us calculate for rest of these. So what you have to do is you have to do this exact same thing. So for B3G applied on sigma 1. Again, you can choose any of the basis function over here. Now if I do that, what I get here is, again, I'm not going to repeat all of this, but here you have to read out the characters from character table, okay? So now if I do this, I will get sigma 1 minus sigma 4 minus sigma 2 plus sigma 3 plus sigma 3 minus sigma 2 minus sigma 4 plus sigma 1, okay? So again, after normalization and cancellation, what you will get is 1 by 2 sigma 1 minus sigma 2 plus sigma 3 minus sigma 4, okay? So now this one is also normalized, and this linear combination, although it is coming from the same s orbitals of hydrogen, but the linear combination will have symmetry as of B3G, okay? So this will transform as B3G, this linear combination will transform as AG, and these two sets will be orthonormal to each other, which is, we know that the irreducible representations are orthogonal to each other, right? So similarly, because these are forming basis for two different IR representations, so they will have to be orthogonal to each other. We can also test the normality or orthogonality condition, which is if you take the coefficients of this 4 sigmas and then multiply with each other and take the sum over all coefficients, you should get 0. So that is, if I take 1 into 1 plus 1 into minus 1 plus 1 into 1 plus 1 into minus 1, right? So the summation of the product is going to be 0. That means these two representation or these two linear combinations are orthogonal to each other. They are also normalized. So what we have got is orthonormal sets of linear combination. So that's why it is called as symmetry adapted linear combinations, because we know the symmetry of these linear combinations. Okay, so let us finish this quickly. I'm just going to write the answers, and I expect that you go back and complete this yourself. Okay, so for P B1U applied on sigma 1, what you will get is 1 by 2 sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. Now this will be orthogonal to the first one as well as the second one, okay? And similarly, if I do P1 P of B2U onto sigma 1, what you will get is half sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. Okay, so you started with 4 basis functions, and you have got 4 linear combinations of those basis functions, which are now defined by a particular symmetry. This is what our aim was, and we will see that this is very, very useful when we go to the next topic, which is chemical bonding. Okay, so far what we have been doing is we have been looking at representations which are only one dimensional representations. So let us also see how to develop SALCs where 2D representations are involved. Okay, so let's take an example. So I'll just put a line over here. So SALCs involving two D IR representation. And the example I'm taking here is PtCl4. Now the first step is to orient the molecule about the axis in the Cartesian axis. So we have central atom which is at the axis, and then you have Cl here, Cl here, and you have Cl here and Cl here. Now the next step is to identify the point group. So point group here is T4H. Right, that is very simple to see. Also, let us list down the symmetry operations of T4H. So you have E, we have 2C4, then we have C2, 2C2 primes, and 2C2 double prime. We have I, 2S4, then we have sigma H, and we have 2 sigma V's, then we have 2 sigma D's. Okay, so now let us quickly write down the reducible representation using the 4 sigmas of chloride atom as the basis. Okay, so this is T4H and this is my tau sigma. Okay, I will label it as sigma 1, sigma 2, sigma 3, sigma 4. Okay, now if I apply E, all 4 sigmas will remain at their position, so that means the character will be 4. If I apply C4, all 4 will change their position, so the character will be 0. If I apply C2 here, again all 4 will change. This C2 is collinear with C4, so sigma 1 goes to sigma 3 and sigma 2 goes to sigma 4 and so on. So C2, under C2 also it is going to be 0. So 2C2 prime. Now this C2 prime is one along x-axis and along y-axis. So in one of the C2 primes, at least 2 chloride atoms will not move. So that means it is going to contribute to 2 towards the trace or character. Right? For the other C2 prime also, it is going to be 2. So the trace is going to be 2 for both of them. The matrix will be different for the 2 C2 primes. Okay, now for 2 C2 double primes, now these C2 double primes are running in between x and y axis. So the trace is going to be 0. I, the trace is going to be 0. S4, again it's going to be 0. Sigma H, it's going to be 4 because nothing will change. 2 sigma V's, it's going to be 2. 2 sigma D's, it's going to be 0. Right? So without having to write the full matrix representation for each of the symmetry operation, what we have done is we have very quickly written by just looking at what s orbital moves under what symmetry operation and so on and so forth. Okay. So now again using reduction formula, we will reduce this to component IRs using reduction formula we get tau sigma is equal to, we will see, A1G plus B1G plus EU. Now you see that these two are 1D representations. So the solution using this, next we have to apply projection operator using this onto any of the sigmas, which we have seen already, and it is very easy to do. But now we will see how do we get this when we apply projection using EU. Okay, so let's go step by step. I'll not be solving the complete thing, but I'll just write down the answers, and I expect that you will go back and solve it. A1G. So I apply A1G onto sigma 1, and the result is sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay, and of course you can normalize it to get half over here. Similarly for B1G onto sigma 1, what do you get is half of, which is the normalization constant, and you will get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. Okay, so because these are 1D representations, one dimensional IR representations, so projection operator will give you only one linear combination, whereas if you use this for projection operator, you should get two linear combinations, because this is two-dimensional representation, right? So now if I do this P EU, I apply projection operator onto sigma 1, what do I get? I will get, and again I expect you to do this yourself, so you will get sigma 1 minus sigma 3. So do this complete calculation, which you know the formula, and the normalization constant will be 1 by root 2 now. Okay, so sigma 1 minus sigma 3. Now how do we get the second linear combination, which will also have the same symmetry as EU? Okay, so there are different methods for this, but there is no unique method to solve this. So what you can do is you can either apply the EU onto sigma 2 and see what you get. Sometimes you may get a second linear combination, sometimes you may not get the second linear combination, and what you will get is simply the previous the first linear combination which you got when you applied this on sigma 1. So when I do this, I do get a linear combination which is sigma 2 minus sigma 4, and I know that this is going to be orthogonal to the previous one. Sigma 1 minus sigma 3. Okay, so I do get this, and both of them will have same symmetry as EU, and but in certain cases you don't get two unique linear combinations, and in those cases what you have to do is, so I'll just write down, for a 2D IR representation we must get two orthogonal, you can of course normalize them, so that's why it is orthonormal, orthogonal functions which jointly form basis for the representation. So these two together will jointly form the basis for EU representation. Now first is as usual, so first is obtained by, first linear combination is obtained by applying projection operator on one of the basis function. Now for second, there is no unique way of doing that. In different point groups, you will see that you will have to adopt different methods. But we recall that any member of the basis functions, or you can say basis set, like sigma 1, sigma 2, sigma 3, sigma 4, all forms function, must be affected by the symmetry operations of the group in one of the following two ways. The first is the basis function will go into plus minus 1 times itself. That means if you apply the symmetry operations onto this one, sigma 1, you will get either plus sigma 1 or minus sigma 1. That is one of the ways. And the second way is the basis function will go into another member of the set, or a combination of members. So what do I mean? Let's say if I apply any symmetry operation on sigma 1, it will either turn into plus sigma 1 or minus sigma 1, or it will go into any linear combination of rest of the members including sigma 1, right? So let us see an example for this one. Let's see if I'm applying E onto sigma 1 minus sigma 3, it gives me plus 1 times sigma 1 minus sigma 3, right? If I apply C2 on sigma 1 minus sigma 3, I will still get, so let's say this, if I do C2, then sigma 1 will be replaced with sigma 3 and sigma 3 will be replaced with sigma 1, right? So that means it is minus 1 times sigma 1 minus sigma 3, right? So minus 1 times. Okay, so that is plus minus 1 times. So this is not very informative because you're getting the same function back. And similarly, if you keep on doing this, so if you see C2 prime I sigma H sigma V, all of this will give you either plus 1 of sigma 1 minus sigma 3 or minus 1 of sigma 1 minus 3 sigma 3. So it will give you plus minus 1 times sigma 1 minus sigma 3. So not very informative. This is not very informative, right? Now let us see that quickly. If we apply, however, if we apply C4 onto sigma 1 minus sigma 3, what do we get? We will get sigma 2 minus sigma 4. Similarly, if you apply C2 double prime onto this, you will get sigma 2 minus sigma 4. Similarly, S4 onto this, you will get again the same thing. And sigma D onto this, you'll get the same thing. Okay, so this is the second orthogonal linear combination that was required. So all it has to do is it has to fulfill the orthonormality condition with the first one. So the first one is obtained directly by applying projection operator. Second one can be obtained by applying projection operator onto an alternate basis function out of that set only. Or what you can do is you can apply different symmetry operations onto the first function, which is first linear combination which is obtained, and see if you get a second linear combination or not. Okay, so this way there is no unique way of doing it because the number of equations are less and the unknowns are more. So that's why we need to go for hit and trial, and this is how it is done. So as and when we come into this kind of trouble, we will see that there can be more unique ways of finding degenerate linear combinations. So these are two degenerate linear combinations because they form jointly basis for EU representation, right? Okay. So here we wanted to have two representations, two linear combinations, and we have got two. So there is no need to go for further calculations here. And I would suggest you to take a molecule, take this as a home assignment. SALCs, where you will develop SALCs for a 3D representation, where you should get a 3D representation. Try to pick up some molecule which has tetrahedral or orthogonal octahedral symmetry and see if you find a 3D representation and you can get three linear combinations which will jointly form basis for a 3D representation. Is left as an exercise. Okay, so that is all for today, and next class onwards we'll be discussing chemical bonding. All right, thank you very much.